Assalamualaikum warahmatullahi wabarakatuh and good day to Dr. Ain. So my name is Nurin Syazana binti Abdullah Hamid, matrix number 207071. So these are my group mate, Maryam and also Umie. So we will be presenting on the topic of cut out wing, chapter 23.8 on the book. So next we will start with this is the example 23.6. So we will be focusing on this example, and these are the question. So it is about a wing consists of 3-bay rectangular section box. So I have highlighted what is given and what is to find in this question. So what is given is torque T equals to 10 kilonewton meter and also other distance in the figure shown after this. And also what to find is we need to calculate the shear flows Q in skin panels and spar webs, and also calculate loads P in corner flanges and forces on each side of the cutout. So we will be looking at the diagram after this. Okay, so these are the diagram that the diagram of the question. So they have bay 1, bay 2, bay 3, and also the front spar and also rear spar. So they also got station 0, station 1500, station 3000, and also station 4500. So this is like similar from the previous lesson for a boom, like they add up the previous section or station. So it's like from the station 0 to station 1500 it is remain, and for the next station they add up from the previous station distance, which 1500 millimeter plus 1500 millimeter equals to 3000. So for the next station they add up from the previous two station also. So this is the cutout section which is at bay 2. And these are the parameters for length and width and also width, and these are the torque. So the steps involved in this question, we need to find the shear flows at skin panel, which is the equation that will be used after this is QSP equals to T over torque over 2 area of the wing. So next we will find the shear loads P at spar webs using the respective equation after this will be shown. And the third step, we need to find the Q1, Q2, and Q3 by using the summation of F force at Y and X axis, also summation of moment. Only then we can get the value of Q1, Q2, and Q3 that will be presented by Nick and Umie. So that's all from me. Thank you.
Assalamualaikum. My name is Nurin Aqiela binti Abdullah. Matrix number is 06646. So firstly, we need to find the shear flows in the skin panel, which is torque over 2 times the area where the torque is applied. So after we substitute the value, we will get the shear flows in the skin panel is 31.3 Newton per millimeter. Noted that this equation only valid if the wing structure were continuous and the effects of restraint warping at the built-in end is ignored. Next, we need to find the shear loads S. So consider this figure B. We can assume that the shear loads in the front spar and the rear spars form a couple at any station in bay 2, which is equivalent to the torque applied. So from this statement, we can visualize it into this equation, which is the distance between the front spar and the rear spar times the shear loads is equal to the top. So after we substitute the value, we will get the shear loads is equal to 12,500 Newton. Next, we need to find the Q1. So for this solution, I use the equation of equivalent in the vertical forces. So we can choose either at the point at the station 1500 or station 3000. Noted that both stations will give the same answer for the Q1. So we substitute the value, which is 200 Q1 plus 12,500 is equal to 0. Then we rearrange, we will get the Q1 is equal to 62.5 Newton per millimeter. Next, we need to find the flange loads P. So for this solution, I use the equation of equivalent in the lower part of the front spar. So we can use either lower part or the upper part. Both part will give the same answer for the P. So substitute the formula, which the value 1500 Q1, the distance from the station 1500 to 3000 plus 2P is equal to 0. Then we rearrange, we will get the flange load P is equal to 46,875 Newton. We need to find Q2 and Q3. So this figure shows the loads on the battery, the shear loads on the battery. So this one is the free body diagram at the point of flange 1, and I use the equation of equilibrium in horizontal forces at flange 1. So substitute the value 1500 Q2 minus 1500 Q3 minus P is equal to 0, and then we rearrange, we will get the first equation, which is Q2 is equal to 31.3 plus the Q3. Next, since we have two variables, we need to create one more equation. So we know that the resultant of the shear flows Q2 and Q3 must be equivalent to the applied torque. So the moments about the center of symmetry at any section in battery is equal to the applied torque. So we substitute the value, which is the moment arm for the Q2, which is 200, times the 800 of Q2 plus the moment arm 200 times the load, which is 800, and Q3 is equal to the torque. Then we simplify or solve this equation. We will get the second equation, which is Q2 plus Q3 is equal to 62.5. Then we need to substitute this formula, this equation 1 into equation 2, and then we will get Q3, which is 15.6 Newton per millimeter. And from this equation, we will get Q2, which is 46.9 Newton per millimeter. And why I times 1500 with Q2 is because the load is equal to shear flow times the distance where the shear flow take place. And for this example, both Q2 and Q3, the distance is equal to 1500 millimeter. So that's all.
Next, for the last step, this is an extra step for find the distribution load at this station. Actually, we need to find the distribution load at each flanges, but for now, we just find at the top flanges at the front spar, at here. This one. Okay. At station 0, the load is 0 because it is fixed at on the fuselage, and then at the station 1500 is this value from the calculation Nick's already calculate. And then for the 2250, it's the middle of the bay, second bay is the middle, this part. So the value is 0 because it the location is at the mid B. At the station 3000, the P is also the same as this one. At the station 4500, the value is 0 because location at the end of the wing. This is the distribution 0 here. And lastly, the things you guys need to take note is the P actually is the same at all flanges, and the difference is just either the flanges in the compression or tension, like this one. Like this one, the P is under compress, this one is tension, this one is compressed, this one is tension. That's it. Thank you.